My name is Vladimir Padnos. I'm Director of Marketing and Support here at TerraAnalysis, and together with my colleague Alex Lebimtsov, we will speak today about new features of the version QuickField 6.1, which was released a month ago in December 2015. As our users know, QuickField originally was a purely 2D package, and here is a list of analysis formulations available prior to version 6.0. It includes magnetic problems analysis, electric analysis, and thermostructural types of analysis. With version 6.0, we included also 3D extrusion electrostatics as a free preview available for all customers who have 2D electrostatics and 2D DC conduction. And now we introduce 6.1, which combines 3D extrusion with new type of new possibility to create three-dimensional geometry in CAD systems and then imported it to QuickField. So today it is possible to create geometry not only as a 3D extrusion but also as a arbitrary 3D geometry made in CAD programs and transferred to QuickField via step file. It's one of CAD formats. So what is the difference? Extrusion means you rise some planar shapes to some predefined distance. And the extrusion model combines the planar shapes and walls. And angle between the plane and wall is always 90 degrees. It is not always good because in majority of electric applications, the surfaces are smooth and transitions are not 90 degrees. It has physical reason because angle causes increase of the field stress and electrical insulation may break down, and this means what majority of practical electrical devices have very smooth surfaces and smooth transitions. It was not possible to do this in extrusion, but now it is possible to have a smooth shapes like shown on the screen in CAD programs, and then they may be imported to QuickField via step file. So today you may use almost any CAD program to create the 3D geometry, then export it to step file and bring it to QuickField. A range of CAD applications is huge. You may use SOLIDWORKS. On this slide you see the operation which required to transfer the geometry to step file as a save as. You select step and you press save and you get the step file. You might do it in FreeCAD. You might do it in Solid Edge. You might do it in Rhino or Autodesk. So in almost any modern CAD package has possibility to export geometry to step file. And 3D CAD import in QuickField make it compatible with all major free and commercial CAD packages. Limitation of our current step import filter is we support one body and multiple shells, but big advantage what you may also add the background region as a rectangular box, which encloses the whole model at predefined distance. And these types of geometries may now be solved for electrostatic analysis. And later today my colleague will show you several examples, including conducting sphere inside applied capacitor, like a air inclusion in the capacitor, bushing insulator with corrugated surface, two mushroom-shaped electrodes, and arcing horns. As you see, these are very complicated three-dimensional geometries, and now it is possible to run electrostatic analysis on these configurations. QuickField 6.1, as usual, is available in several editions. Student edition has limited number of planar and limited number of three-dimensional nodes, but it is free. It may be used by anybody for any types of application, as long as you are fine with our mesh limitations. Light edition is a site license with some limits on planar mesh node number and no artificial restrictions on 3D mesh node number, and it is available for academic organizations, for universities, as a site license, helping students to study a variety of electrical and physical classes. And professional edition has no artificial mesh limits for 2D or 3D simulations. Our future plans for 3D development include expanding set of our 3D formulations. Currently it's only electrostatics. We plan to add DC conduction and thermal formulations in the near future, and then continue with magnetics, time harmonic analysis, and transient types of analysis. So QuickField 6.1 continues our traditions of very fast and efficient finite element software and brings more for customers who need 3D analysis, in addition to our proven 2D analysis suite. Now my colleague Alex will continue with showing you examples in live presentations with QuickField 6.1. Alex, please go ahead.
Thank you, Vladimir. Today we will review 4 cases: the conducting sphere inside the plane capacitor, the bushing insulator, the case of 2 electrodes placed in the space, and the arcing horns. Why should I need 3-dimensional analysis for the plane capacitor? There is the analytical equation to calculate the capacitance in this case. I will create the new problem, specify the location of the problem files and the problem name. The problem type is electrostatics and the model class is plane parallel. For the plane parallel model class, I should specify the model depth. Effectively, I should specify this dimension. (0.1 meter). Here there is the geometry model editor window, and I should build the geometry model here. This is one of the plates, this is the second plate. Now here is the geometry model. Then I should assign some labels to geometric objects. For example, this is the dielectric. This is the plate with positive charge. And this is the plate with the negative charge. Once I have finished with the labeling objects, I may assign the physical properties to each label. The labels are listed here in the tree. For the dielectric, I specify the electric permittivity of the material. In my case, it's 4. For the negative charged plate, I specify electric potential. For my case, it's -5 volts. And for the positive plate, I specify +5 volts. Now, everything is almost ready. I should build the finite element mesh, save all problem files, and run the simulation. And here you can see the field distribution inside the plate capacitor. I will adjust the field picture and switch on the vectors and the color map. Now you can see how the electric potential is distributed inside the capacitor and how the electric field strengths vectors are distributed. But my task is not only to simulate the field distribution inside the capacitor, but also to calculate the capacitance. There is a simple equation to calculate the capacitance. You should divide the charge by the potential difference. So I will build the integration contour. I will close the contour around one of the plates and calculate the electric charge stored on this plate. Now, if I divide the electric charge by the potential difference, I will get the capacitance. And you may check these values against the analytical solution. In analytical solution, I should multiply the electric permittivity of the dielectric multiplied by the electric permittivity of the free space multiplied by the plate area. 100 by 100 millimeters will be 0.01 square meters, and divide by the distance. In fact, the distance in my case not 5 millimeters but 10 millimeters, so it's 0.01. So this is 45.4 10 to the power of -12, because the permittivity of vacuum is 885 10 to the power of -12. So you can say I get the same value with QuickField. But plain capacitor is not that plain. There is the fringe field at the edge of the capacitor. And if I'm interested in simulation of the fringe field, I should add the air outside the capacitor. So I will let the field distribute outside the capacitor. This block will be the air. And the electric permittivity of the air is 1. Now I will build the mesh again and run this simulation. You can see the field is built outside the capacitor. And if I again measure the charge, You may note that the value is different from the one I measured when there were no fringing fields. But that was the two-dimensional simulation, and I take into account fringe effects on the top and on the bottom side of the plates, but there are similar effects on the front and on the back side of the plates, and I cannot take into account these effects in two-dimensional simulation. So eventually I have to run the three-dimensional analysis. I will change the problem type to the three-dimensional extrusion. And once I have done this, I can switch between two-dimensional and three-dimensional view. Now this is the three-dimensional model. But if I run the simulation now, again, I will take into account the fringe effects only on this side. To take effects here on the upper and in the bottom, I need to add the air block at here and here. So again, I switch to the two-dimensional model and add heights to objects. Here it is. Now I should assign label to each object. This is the air. And below the capacitor is the air too. This is the air block. This is the dielectric block, this one inside. And outside is the air block. I have the negative plate on that side. I have the positive plate and the air outside the capacitor, so I can take into account all the fringing fields. The next step is to build the finite element mesh. Here you can see the finite element mesh. I can use cut by plane tool to show you the mesh inside. And this is how it looks inside. Now I can save problem files and run the simulation. Again, I will use the cut by plane. You can see the fringe fields here. And if I change the cut plane position, you will also see the fringe fields here. So now I will take into account all the fringe effects in the plane capacitor. And again, my task is to calculate the capacitance. I will use the simple approach. I will select all the bodies and calculate the stored electric field energy. And we know that the capacitance value is the twice this divided by the potential difference square. So you can see 3.8. It was 3.5 in the ideal capacitor, but in real capacitor, the capacitance differ from the analytical value. And with QuickField three-dimensional analysis, we can calculate the real capacitor capacitance. Now that was the extrusion introduced in QuickField 6.0. But let's imagine that we have some defect, some inclusion inside the capacitor, some spherical or small radius. How should we simulate this? Well, let's switch back to QuickField. Now this is our geometry model, and here I should draw the defect, some cylindrical body. Yes, that's simple. Now I switch back to the three-dimensional. I will switch on the transparency. Here you can see the cylinder. In fact, I have the small bodies, small inclusion, so I should assign heights, more heights to the cylinder. Again, I switch back to two-dimensional and specify the heights for my inclusion. From 0.5 to 0.6. Switch to three-dimensional. Switch on the transparency mode. Here it is. This is my inclusion. But you can see that the shape of this inclusion is not spherical. It's cylinder. I may adjust the height of this cylinder. But nevertheless, it is small, but it's a cylinder. With extrusion, I cannot generate this spherical shape. I cannot generate the cone or toroidal shape. QuickField 6.1, it is possible to import the geometry model from the majority of the computer-aided design programs in QuickField. This type of geometry model is not compatible with the extrusion, so I have to create a new problem, or I should change the problem type. So this is not three-dimensional extrusion, this is the three-dimensional import. And the model type is not more the MOD, but the M3D. So this is the three-dimensional model which supports importing the geometry. I will press the import button and locate the file. this is the file that contains the three-dimensional model in step format. Here is the imported model. And if I look inside, again, I will switch on the transparency. You can see there is indeed this spherical object inside my capacitor. Now again, I should assign this labels to the objects. This is the dielectric. This is the negative plate. This is the positive plate. And if I hide the dielectric, there is the sphere. The air has permittivity of 1, while the dielectric has the permittivity of 4. Now let's show all the objects. I have the air sphere inside. I have the dielectric and positive and negative plates. Now again, I should build the mesh. And here you can see the finite element mesh. Again, I will use the cut plane to show you how the mesh looks like inside the capacitor. And we can save all problem files and run the simulation. And this is the result. We have the electric capacitor with the spherical part placed inside. This is the spherical part inside. To highlight it better, I will switch to the electric field stress color plot. A bushing insulator is used to insulate the conductor, it is shown with red, that carries the current at high potential from the grounded wall. In case we need to put the conductor through the wall, we use the bushing insulator. The insulator insulates the conductor from the grounded wall. Effectively, there is some electric stress distribution inside the insulator and along the insulator surface. And our task to calculate the electric field stress distribution, find the weak places inside the insulator, and find the electric field distribution along the surface. As you can see, this model features smooth curves, so I cannot simulate it using three-dimensional extrusion. Instead, I will use the three-dimensional import feature of QuickField. So I will start QuickField. Here it is. I will open the problem properties so you can see what's the problem type. The problem type is electrostatics. I need to calculate the electric field distribution. And the model class is three-dimensional import. Now let's take a look at the model. The model is loading now. Here you can see it. You may note that this is not the insulator itself. Indeed, the insulator is placed inside the background region. I will make this region transparent. So this is one of the features of QuickField 6.1 is that you can import the body, the insulator, and build outside this and put this body in the rectangular box. So effectively this insulator is placed inside the air. I use this background box to simulate the air outside the insulator. Next, I should assign the labels to the objects. There are two objects in my model, the insulator with dielectric permittivity of 2.2 and the air outside with dielectric permittivity of 1. There are also the high voltage sources, high voltage faces. It's the conductor's surface as it goes through the insulator. So inside this tube there is the high voltage. And as we can see from the picture, here is the grounded wall. So this surface is grounded. This is the grounded surface. Once the labels are assigned, we should build the finite element mesh. You can see it now. And I can use the cut plane tool to show you how the mesh looks like inside. Now, once we have finished contemplating this picture, let's take a look at the simulation result. Here's the electric potential distribution. I will hide this air box and take a look at the electric potential distribution along the insulator surface. Inside is the high voltage conductor with electric potential of 10,000. And here is the grounded wall. But I am interested in electric field stress distribution along the surface and inside the insulator. So I will select this profile and switch on the XY plot. Here is the electric potential distribution along the surface of the insulator. And this is the electric field stress distribution. Here is the place where the insulator goes through the wall. Now that was the electric distribution on the surface. Now let's take a look inside. I will use the cut by plane tool. And switch to the two-dimensional view. I will adjust the field picture. This is the electric potential distribution, and I would like to switch to the electric field stress. Here on this color map, we can see that this place of this part of the insulator is the most stressed part. We can see the same picture on the three-dimensional view, of course. I will hide the cut plane and switch on the electric field stress and the vectors. This is the case of two electrodes placed in the tank, and our task is to calculate the electric field distribution between these two electrodes. We know that the electric permittivity of the air is 1, and that the voltage difference applied to these electrodes is 1 kV. I will start QuickField. Again, let's check the problem properties. This is the electrostatics problem, and the model class is three-dimensional import. Let's open the geometry model and take a look at it. There is no background region here. This body is the imported using the card importing from the card. And this is the air block. But inside this air block there are two electrodes. We do not need to simulate the metal electrodes. There is effectively no electric field inside the conductors. So we simulate only the air block and specify the electric potential distribution on the electrode's surface. This is the negative electrode, and this is the positive electrode. Now let's build the mesh. And take a look inside and see how the mesh looks inside. Now along Y, yes. I I will hide the cutting plate. So this is the finite element mesh distributed in the A space. In fact, the mesh size is small. It's only 3000 nodes of elements, and I'm using the student QuickField, which is available for free download from our website. So all these examples you see today, you can simulate with the free QuickField Student Edition version. Now let's take a look at the simulation result. Again, without cutting a plane, I cannot see the field distribution inside. I will switch on the vectors and hide the plate. So here is the electric potential distribution with the vector plot of the electric field strength. And of course I can switch on the color map of the electric field strength, and I can measure the electric field strength at every point. This is the point coordinates, and this is the electric field strength at this point. I'm using the probing mode tool. Now let's move to the last example. This is the arcing horns added to the bushing insulator. The purpose of this device is to protect the insulator. This insulator is designed to withstand the voltage of 6 kilovolts. But in case of lightning or some defects on the line, the voltage can rise above these limits. And to protect this insulation surface from the surface current from the discharging along the surface, the arcing horns are invented. So in case the voltage is higher than the designed value, there is the arc between these horns. There are too many objects here, but still it is possible to simulate this device with QuickField. So I will start QuickField. And this is the geometry model. Again, I use the background region, the square box, to simulate the air outside the insulator. I will make this region the transparent one, So you can see what is placed inside the air box. In fact, I have only two objects. I'm not interested in the electric field distribution inside the conductors. So I have only the insulator, the air outside, and the high voltage. Now this is the high voltage, this one, surface of the conductor, and the grounded conductor. Now let's build the finite element mesh. Here it is. Let's look inside. Just to check what the mesh looks inside. This is the finite mesh distribution inside my model. Now let's take a look at the simulation result. Again, I will hide the air box. And this is the electric potential distribution along my insulator surface. I may adjust the field picture and switch on the vectors. So you can see how the discharge paths will look like. And I can switch on the electric field strength distribution. I'm interested in electric field strength in the air, so I will unhide all objects and use the cut plane. This is the electric field stress distribution in the air, near the arcing horns tips.